Okay, so good afternoon, everyone, again. I thank you for joining us here today. We're here with Professor Carlos Cuevas, who's going to be leading a workshop on system designs. And without further ado, I'll allow him to speak a bit about himself, as well as go into the details of the workshop, just because we do have a lot of material to cover. If you have any questions, feel free to raise your hand or place it in the chat, and we will definitely work our way to getting to responding to them. So without further ado, Professor Carlos Cuevas, the floor is yours. Thank you. And I've also allowed for share screen should you need to share anything, okay?
Awesome.
Thank
Thank
you.
you. Hey, everyone. Yeah, thanks for being flexible and allowing me to do this virtually. Coronavirus is still around. So yeah. Okay, so I'm going to try to share. Bear with me as I figure this out. Okay. Cool. Can everyone see what
Yep,
I'm sharing at the moment?
all good on my end, yes.
Awesome. Okay, cool. So I'm Carlos. I teach here, Brooklyn College. I have almost 10 years experience now working as a software engineer. I've worked at small startups. I've worked at medium-ish, big-size companies. And I've noticed a trend where an interview that used to only be given really to more senior engineers is suddenly become much more popular to give to even entry-level engineers. And so I thought this would be a really good topic to just give a very introductory, I can't really go in too deep in any one particular topic because each topic in here could be its own entire lecture. But I'd like to at least give folks some of the vocabulary that they could use and maybe sort of a starting point on how to get started to prepare for a systems design interview. So let's move forward. Cool. So typical software engineer interview is usually going to be broken up into a few different rounds. And one that's almost always going to be there is something like a data structures or algorithms type of interview section. So you'll get, any question that would probably be fair game within like an algorithms class. So LeetCode, I have a link there, is a website that has just a giant collection of these types of questions that you can practice. It's freemium, so you can use a bunch of the questions for free. I've done a lot of practice on there. It's extremely helpful. And analysis of algorithms, or whatever the course is called now, probably be a pretty good like precursor for that type of interview. And then there's like behavioral interviews, which are pretty typical, right? Tell me about a time you disagreed with your boss, or tell me about a time when you faced some particular problem. I think those are pretty easy. You just have to like say the answer you think they want to hear. You can read out more about that online elsewhere. So what I'm going to focus on is this third section, systems design. You're going to be given, actually, let's go to so you'll be given a really broad problem, right? It'll be something like design a system that accomplishes X. So for example, design YouTube, right? And that might be the entire prompt that you're given. You're not given this ultra specific question. You're given just, here's a system I want you to design it. And so it's on you to narrow the scope as much as possible and really shrink that down to something manageable. But this is sort of more of a typical what I talk about when I'm talking about systems design. It's a question kind of like this. So many systems have overlap. And what I want to do here is cover some of the basic concepts and components of these large scale systems, because that's also where these things tend to get really interesting. It's in the beginning, it's just like, design YouTube. Well, I'm designing YouTube for 5 users. That's a pretty easy thing to do. If I'm designing YouTube for 10 million users or 100 million users, that's a very different task. And so that's really where system design starts to get interesting, when you have to scale up or handle large loads of traffic. So sort of a very start out basic idea, the idea of a client server model, right? And so this is the most popular or sort of standard way that basically almost every web application works. Clients, right, are a mobile phone, a desktop, the users. They send requests to a server. Server can just be some sort of application sitting somewhere waiting for these requests to come in and responding to them. And every time you've ever used the website, right now we're using Zoom, right? There's some Zoom server and we're all the Zoom clients and we're all sending requests to Zoom. Zoom is responding to those requests. We're using a client server model. Every time you've ever opened up any web application in your life, you're using some version of this client server model. So when I say a request, right, what does that mean exactly? And when I say a response, right, what does that mean exactly? Like, well, let's drill in a little bit into this idea of sending a request and receiving a response. So let's imagine we have a weather application, right? Something I'm just, purely for the sake of example. So what might a request and response look like for a weather application hosted on the web? So the request, first, where do we send this request? Like, it has to have a destination, right? So in this case, I'm going to say weatherinfo.com/weather. That's, again, not a real URL, or maybe it is, but for the sake of this example. So how do we send a request to this URL? So within HTTP, there are different methods. I don't want to go too far down into this, but essentially when you send a request on the web, it has some verbiage attached to it that specifies to the server what type of request it is. So in this case, a GET request means I want you to give me some information. I want to get some information from you. And then how do we tell the app the location for which we want the weather? So people have seen this, I'm sure, when you go to like different URLs, sometimes there'll be that little question mark, and then there'll be like a, sort of a key value pair attached to the end. And so in this case, we're going to say, I want to attach that zip code to this URL, make that part of my GET request, and then I'm going to get the weather for that zip code. And then what might the response look like? It's going to be some sort of formatted data that has some sort of structure to it. So in this case, let's say I'm going to use JSON, which is the most popular way of exchanging data on the web. Right, and so it's using JavaScript object notation. So we're going to have a little brackets and then a few key value pairs, temperature 76. I wish the humidity was 40 and there's no precipitation. So all of this together, what I'm kind of describing is what I would call an API, or application programming interface. So this is a set of rules and protocols that allows one piece of software to interact with another piece of software. So how does software communicate? I don't know if I can quickly jump back and forth to the chat, but I'm curious if folks have any experience with using APIs in their previous experience. Maybe drop a message in the chat, like saying, I've used such and such API. I think one that most people probably would have used at some point in the past might be the Java API, right? The sort of standard library. So now that I've described what an API is, right, let's make this a little more formal. So usually an API has some sort of documentation somewhere, right? So somewhere on the web, I'm going to have a page that says, here are the different URLs that you need to make requests to. Here's the type of HTTP request you have to make. Here are the parameters that you need to provide to me. and then here's what I'm going to respond to you with. So it's this formal contract saying, you send me a request in this shape, I'm going to send you a response in this shape. There's some Java code that would make that request. Again, basically doing what your browser would do when you put in a URL in the address bar. And then again, here's the response in JSON. And then this is another interesting part. This is the code that whomever is creating this API would be responsible for writing, right? This is the code that is, a request has come into the server. The server says, someone wants the URL. Someone wants to get the weather from /weather. That URL would be mapped to this function somehow. Again, I'm kind of outside the scope of this. And this function would be invoked and respond to that request. And here I have this get weather data function. That's just my magic function that does something under the hood. You don't need to worry about that. So again, what exactly is a server? It's a term that gets overloaded quite a bit. Sometimes when we say server, we're talking about hardware, right? The physical box that that some software is running on. And that software we're talking about is also server software. And so this is where the overloading comes in. Sometimes server means hardware, sometimes it means software. So what a server software is it's a process that's listening for requests and responding to those requests. Again, sort of serving up a response. And just to make things even a little more confusing, right? When I say a physical computer, could be a physical computer, could also be a virtual machine or a container, could be some sort of cloud service. So this notion of like the hardware has become a little fuzzy over time, but essentially I just want to distinguish between the software that's running and sort of the platform that it's running on. Those are both can be referred to as the server. So here's some examples of server software. We have web servers or HTTP servers, right? The two most popular ones, Apache and Nginx. But then there's also file servers, there's email servers, there are database servers. So in these cases, these are all, again, software that run on physical servers or run on cloud machines or whatever. And their job is just basically to sit there, listen for an incoming request. In the case of, let's say, Microsoft Exchange, right? I send a request in a particular shape to a Microsoft Exchange server. It knows how to take that request, do some stuff to it, and then fire off a message to someone else, and then respond to me and say, yeah, we sent your email, you're good. So just to make it even a little more confusing, right? So,
Carlos,
yes.
sorry, I just wanted to say we have some comments in the chat, and
Oh, cool.
so are you able to see it, or should I read it out? Well, just for
Let
everyone,
me.
Oliver says he's used it once to deploy is it Kubernetes container?
Oh, okay. Yes,
The
Kubernetes.
API, yes. Oh, Kubernetes, excuse me. And Cindy says she's used it, Spotify for a project. And then Constantine actually asked, and I'm not sure if you'll be covering this, but or if it's under your scope, but if you'll be able to talk about the difference between web server and app server.
Fantastic question.
Okay.
I'm going to
And
talk about that right
great. I'll
now,
just
actually.
chime in whenever I see some, movement in the chat. Go ahead.
Thank you. Yeah, I see it now finally on the side here.
Okay,
This is my
great.
first time using Zoom for anything like
Oh,
actually using.
wow. Okay. Okay, got you.
All my jobs always use Google for whatever reason. So, okay. Um, right. So, Constantine, I'm going to get to your question. I'm going to work it in here. So, the hardware and software can come together in this sort of interesting way where you have your physical server can run multiple server applications or multiple pieces of server software, or you could have separate physical servers, each having their own software. It's pretty flexible. So whenever you hear someone say like the server is down, you might need to specify what is the specific thing you're talking about? You're talking about the file server that's on, physical server 1, or you're talking about the web server that's, on physical server 4, or whatever it is. And so here's where we're going to talk about this idea of like an application server versus a web server. So the standard sort of really basic model is, you have your client, you have your server, and your server again could run multiple different pieces of software or just one. In this case, I have a single server. It's running my application and it's running a database. So there's a bit of fuzziness here with the difference between a web server and an app server. Generally, the app server is going to be running behind a web server. So if I could somehow I don't know if Zoom would let me, I don't know if it's gonna let me do that, but I don't know if there's like a laser pointer or something like that, but essentially this application, this blue box here in the server, it's going to do both. You're going to have in front of it a web server that then takes those requests and passes it off to your application. I'm going to make this more concrete also as we go forward, but for now, sort of think of them as two in the same. But it's a little fuzzy. So again, I don't need to run all of my server software on one physical server, right? I could have an app server running my application. I could have a database server running my database, right? And have two different physical servers here. And again, when I say physical server, that could mean the cloud, it could mean two virtual machines running on the same button. It's a little fuzzy, but idea is I can split these things up into their own little containers or boxes or whatever. Can someone guess, or maybe someone just knows, why would I want to do that? Why would I want to split up my application from my database or have them running in two different servers or instances?
You can also unmute yourself or raise your hand if you'd like. But someone, I think Constantine said, I don't know if this is in response. Constantine, feel free if I'm incorrect. Fault tolerance or app server, is that correct?
That is correct. That's part of it. We're going to get to that as well. Another
Anyone
part of it.
else?
Oh yeah, but you're on the right track. Okay, I'll move forward. Scalability. Okay, that's the other one that I was looking for. Right. So when we talk about scalability, what do we mean? Can we handle more traffic? Can we handle more users? Can we handle a larger scale, larger volume of data or transactions or whatever it is? And by splitting things up like this, I can add more app servers, I could add more database servers, and they don't have to be sort of perfectly in sync with each other. There can be more of one than the other. Keeping things modular like this allows me a great deal of flexibility. So when we talk about scaling, usually we're talking about two different sort of axes. You can scale vertically or you can scale horizontally. Vertically just means I'm going to get a more powerful computer, right? So I have, the third strongest computer in the world. I'm going to buy the second strongest computer in the world. Like add more RAM, add more CPU, add more whatever it is. Whereas horizontally just means I'm going to add more computers. There are pros and cons to each, right? But generally, when we talk about scaling, we're usually going to be talking about horizontal scaling. So why is that? So there's a limit on how much you can scale vertically, right? After you've maxed out the most powerful CPU in existence, then what? What do? You can't just, well, that's the most powerful CPU, right? Like, so you can't go any further up. Whereas horizontal scaling, it's essentially infinite. I can always just add yet another instance at the end. So it works though only in certain contexts. And so I'm sure everyone's familiar with this notion of parallelization, right? And so let's imagine you have 10 washing machine size bags of laundry to do. Right, so if I have one washing machine, we do one at a time. Right, but if I have 10 washing machines that I can run in parallel, that means I can do all of my laundry in the same time it would take me to do just, if one washing machine, if I only had the one. So horizontal scaling is just adding lots of washing machines. And that's generally the approach that folks will take to scale on the web. Okay. So a little bit of a rough transition for this slide, but it'll start to make sense. In order to facilitate scaling, there's a few things that we have to have in place, particularly horizontal scaling. And virtualization and containerization is one of these concepts. So when you install a piece of software directly on your computer, you're running that software on what we would call bare metal. And essentially, there are the fewest amount of layers between your application that you're running and the physical server that it's running on. So let's think about, when I installed Zoom on my laptop, Zoom is the application, the operating system, right, is going to be Mac OS, and then the physical server is going to be my MacBook. That Zoom application has very direct knowledge of the operating system it's running on. It has sort of direct knowledge about the physical server that it's running on, right? When you install Zoom, generally you're going to have to choose like the version that corresponds to your operating system. Sometimes when you install a piece of software, it'll even tell you like you have to specify which particular type of CPU you're using. So every time you saw something in bare metal, there's a bit of like a coupling that occurs between that application and the context that it's running in. And that's sort of the segue for this idea of virtualization, which is there a way we can add in some middle layers between the software I'm running and the context I'm running it in, such that that software could then run basically anywhere? And so with a virtual machine, your application is going to be bundled with the operating system that it's intended to run on. And that's going to be its sort of own independent package. And then sitting between your virtual machine and the operating system that it's actually running on is this layer we call the hypervisor. And don't worry too much about the details of this, but essentially just know that there's a middle layer that's going to abstract away the platform I'm running on. It makes the software think it's running in this on its own little computer that doesn't actually exist. It's a virtual environment. And then containerization is just like an extension of this idea. Again, I don't want to go too far into any one of these things, but I just want you to be aware that there is, again, a sort of isolation and independence of the application that I'm running and the operating system or the physical server that I'm running it on. I have this sort of independent unit that can just be plucked on and off and run in any context that I want, so long as I have that container engine sitting underneath. And same thing with virtualization, I have that hypervisor sitting underneath. I can run this on any platform. So I'm thinking of the example of, again, like if I want to run some Windows application on my MacBook, I could use something like virtualization, right? Where I am installing this application, it thinks it's running on Windows, but underneath it's actually running on a Mac, because again, that virtual environment is tricking me into working how I want it to. So, and I want people to drop some comments, right? Which of these two cars requires more knowledge of what's under the hood to operate, right? And should be a very obvious answer, right? So the one on the left looks almost like the cockpit of a plane, right? I've got a million different gauges and knobs, and I've got all these little switches, and I probably have super fine-tuned control over everything that's going on under the hood. Whereas on the right, I have this ultra minimalist sort of dash that I just have a steering wheel. right? That's all you really see there. So if you had to guess, so let me get some messages in the chat, left or right, which one requires more knowledge of what's under the hood to operate?
Okay, someone says right. We got more right hand side.
Well, so maybe the yeah, left, right? So
Someone
it's
says
actually,
left.
yeah, right? So in order to operate the car on the left, right, I have to know how to tweak all these knobs and pull all these levers and, right, presumably, just and sort of intuitively, right? If I put you in the cockpit of a plane, I imagine that requires a little more information than if I were to put you in a golf cart, right? Because again, a golf cart's interface is really simple. And so this idea is abstraction. It's a really powerful idea. It's very common within computer science and programming, and it's the idea of hiding details, right? The car on the right, the minimalist interface, is hiding all of the details underneath of how the car operates. You're just turning a steering wheel, right? Whereas the car on the left does not hide very many details at all. If again, assuming it were an actual car, these are both terribly AI generated images. So why would we bother doing that? So again, sort of, which of these is easier to use? If you were to guess, right? The one that's more minimalistic, that hides all those details, is much easier to use for the user because it reduces complexity. It also increases portability / looser coupling, right? So again, going back to this, if I were to train someone on how to drive and they were using the car on the left, and then I dropped them into another car that looks like the car on the left, but all of the knobs and gears and switches are in slightly different places, or one knob has a slightly different meaning than another. Whereas if I were to take someone who learned how to drive the car on the right, the minimalist car, and drop them into another minimalist car, they'd probably be fine, right? And so this ties into this idea of like containerized applications and virtual machines, right? It's a layer of abstraction between your application and the context it's running in. So it's a bit more like running in the minimalist car versus the car that would be sort of tightly coupled or has its sort of tentacles deeply woven into the the context it's running on. These containerized applications can be just spun up and down, and they can be run in all sorts of different contexts because they don't really care about what platform they're running on. As long as they have that sort of container engine or the hypervisor sitting beneath them, they're good to go. And so why am I talking about all this? Because if we want to scale horizontally, right, I have to be able to add more app servers. And so for me to be able to do that, this is where, like, do I want to spin up 4 or 5 physical servers every time I want a new server? Probably going to want to use some sort of cloud or container engine, something like Kubernetes, to just spin up a bunch of containers. And now I have 4 times the bandwidth that I had before. I can handle 4 times as much laundry as I could before. Docker, yes, so Docker is from one of the comments, Docker is a container engine. It allows you to create these containers. Kubernetes works with containers as well. So yeah, so this is how we scale horizontally, right? We're going to just add more servers, add more laundry machines. But now what, right? This kind of introduces another problem, because I have clients sending requests to these 4 different servers, but which server gets the request? Or do the clients have to know that there's 4 different servers? What if I had a 5th server? Do I need to update all of my clients, all of my desktop apps or my website? Or so now, as we start to introduce these things that help us with performance, we start to add this overhead and this complexity that we have to handle. And so this is where the notion of a load balancer comes in, right? So the requests come into a load balancer. The users are none the wiser about where these requests are going. They're just sending a request to google.com. But what you're actually sending a request to often is a load balancer, which is then going to distribute those requests across all of your different app servers, and those servers will be in a cluster of some sort. Again, generally on like something like AWS or GCP or Azure. And so the load balancer will worry about making sure that no one server is overloaded, or it'll just do like a round robin. There's a bunch of different schemes that you can use for load balancing. Again, every one thing on this slide could be its own lecture, if not entire class. So bear with me if I skip over some details. But yeah, so load balancing is really important, super powerful idea, and is almost every semi-decent scale website you've ever used is using some sort of load balancing behind the scenes. So someone mentioned, I think it was Constantine, right, talked about fault tolerance. And so that's the other sort of really big virtue of being able to have this sort of system where you have distributed processing, right? You have more than one server running, and you can switch between them. Let's imagine a scenario where a user sends a request to the load balancer sends it off to one of our servers, but that server is actually crashed. So now what? Well, we can handle that pretty well now, right? Because we have redundancy, we have extra copies of our application running. So we can just try another server within the cluster. So not only are we now able to handle more load, we're also able to handle failures and be a little bit more resilient because we have this redundancy. So again, it's really, really powerful thing. At Etsy, servers would go down all the time and people would be none the wiser because we had so much redundancy. Super, super powerful idea, but again, adds a lot of overhead and a lot of complexity. Another consequence of wanting to run all of these different applications sort of side by side, right? We have to design our APIs in a kind of a specific way. And so there's something called a RESTful API. It's a style of API design. It's not like, it's not super strict about like, this is what it must be. It's a style of API design, some guidelines, some principles. You can read the RFC, I think, for it online if you want. It's pretty short. But the idea is we're going to use HTTP methods and sort of the different verbiage that the HTTP server can give you for sending requests to access server data. And we're going to do it in a stateless way. So what do I mean by stateless? If you go to your corner store and the guy at the deli counter knows that you always order the, turkey and Munster cheese sandwich or whatever, I would describe that as stateful, right? I walk in, I don't even have to say anything. He knows who I am, and he knows that I want that sandwich. May or may not be based on a true story. Stateless would be, I come in, I have to dictate exactly what my order is. This person will pretend as if they've never seen me before. They will only process what I'm saying in terms of what I'm saying at that particular moment in time. And that's what a stateless API would be. Each request is processed purely based on the information provided within that request. The server doesn't remember anything about previous requests. The server can write to the database, that's fine, but what I'm talking about is a little different. And so I'll get to that in a second. Constantine asked about caching. We're going to get to caching. But again, right now, I'm just talking about my API. I'm not talking about my entire application, right? Every application is going to have some statefulness, right? So, if I sign into Google, I expect to see the emails that I had the previous time I was here, right? And that's fine. That the application has a state, but the API doesn't have a state. a subtle difference, but it's a pretty powerful thing. So why does statelessness matter? Well, we're looking at this graph now, right? If our API is implemented at the application layer, and now we have multiple copies of that application, well, then I can take a request and I could send it to any one of those applications within my server cluster, right? I'm not stuck with one particular instance the way that I would be if there were a stateful connection between those two. So again, really, really powerful. I can just kind of slap on lots of more servers. I can cut down the number of servers. It has a tremendous amount of flexibility because every request has everything it needs to be processed. Don't need to rely on the application server remembering a particular thing about a request. So yeah, since each request can be treated independently, a request can be routed to any one of the servers. All right, so we've scaled up our servers. We have our load balancer. Anyone else want to guess, just looking at the picture? What else can we scale up? No guesses? DB, yeah, DB. Right, so I can scale up my application, but what if my application now is hitting a point where my database is starting to go really slow? So next obvious thing to do. So something called database replication. And again, I'm kind of getting a little creative with my pictures here, so please bear with me. But that server cluster here in this slide, same sort of server cluster in this slide, right? There's a bunch of different ways to do this. This is not just the one way to do the database replication, but this is the simplest one for me to explain. My server cluster will make all of its writes to one primary database. That primary database will then propagate those writes to backup copies of the database. And then so eventually I'll have everything nice and in sync, and the same data will live on all of my database copies. And then if I want to do a read, well, I don't have to read from the primary database, right? Because the same data is going to be spread across all of my backups. So now I can do that same parallelization. I can do that with my reads from the database just the same way that I could do it as requests from my servers. And so the reads will come across all the different instances to the server cluster. And then now I can actually scale up my database to be able to handle much more reads than I could before. There are also different ways to do it. Again, like don't have to actually write to just one. You can write to all. There's a bunch of different schemes, but again, this is just sort of the simplest one. And then the same idea, right? Database replication, just the same way that it helps with performance. It also helps with availability, just the same way that having redundancy in your application server and redundancy in your using a load balancer, right, can help. So let's imagine a write fails to my primary database. So now that write can't propagate to any of my backups. Well, what can I do? Promote one of those replicas from secondary to primary. And then now, within no time at all, I'm back up and writing. And then that crashed primary database, the old one, I could just kind of take care of that and figure it out after the fact. So again, helps a lot with performance, helps a lot with availability, but now there's a lot of complexity I have to manage. I have several different copies of the database that I have to worry about, and worry about things being in sync with each other, and it introduces a whole new host of problems, but it's really, really powerful for when you need this type of scale. Okay, now I've got my app server, scaled up. I've got my database replication set up. What else can we do? What more? Someone actually already said it in the chat. I gotta. It's still not fast enough. I need more speed. Let's see who said it. Constantine said it before. Right? Caching. Yeah. Right. So databases are fast. They've gotten very fast. but compared to, but that we can do better. And so this is a sort of a way that I like to think about it, right? There's this sort of hierarchy of memory. When you're dealing with your CPU and you're doing any sort of calculation, the fastest possible location for any data to be is in the CPU on the registers within the processor. They're extremely fast, but you only have a few of them because they're very expensive. As you work down this hierarchy, things become less fast, but cheaper and more available, right? And you can kind of think about databases as being, and not to say that they're slow, right? But they're sort of toward the bottom of this, right? It's reading from the database is sort of the worst case scenario in a lot of situations because databases have a lot of overhead. So just the same way it's faster to read from RAM than it is to read from the disk, it's going to be faster to read from a cache than it is to read from the database. So what's a cache, right? It's basically a super simple version of your database that's going to sit between your server cluster and your database. Again, this picture is a little misleading because there are a bunch of different ways to implement caching. There's write-through caches and pass-through. But for the sake of simplicity, let's imagine whenever the server is going to write some data, again, you signed in and you made a purchase or something like that. So we're going to write that to the primary database. Then you sign back in an hour later, you want to check in on your purchase. You want to see, what's the status of it. So the server is going to try to read from one of the databases and show you that information. But if we could keep that information cached, so again, sort of keep it in, let's say, memory, as opposed to reading it from the disk, or keep it in this copy of a sort of tiny copy of the database. It's a lot faster to read from, rather than having to go through all the data that's in our database. It's going to make things a lot faster. And so this is where caching comes in, something like Redis or Memcache. So why are caches faster than database? Again, they're designed to be fast to read and write from, tend to be like very simple key value stores, whereas like a relational database, right, has a lot of constraints. It has sophisticated relationships. It also tends to carry a lot of data. A lot of caches will store their data in memory instead of on the disk, which again, memory is faster than the disk. And then just as a side note, you can also scale up caching as well, horizontally, I should say. Cool. Okay, so now we've got caching. What are proxies and reverse proxies? That's a little in the weeds than I wanted to go. I'll quickly say a reverse proxy is usually something where you set up a web server to sit in front of your application, and then the requests go to that web server instead of going directly to your application, such that if the web server crashes, right, you're not crashing your application. We could talk to me about that after or something like that. That's a whole different topic, but that's very much related to a lot of what we're talking about. But yeah, so anything more we can do, right? We've scaled up our servers, we've scaled up our database. Now we have caching. I'm still going to say there's still more we can do to make this faster. And I'll give a hint. It's sort of very much related to caching, sort of caching at a different spot. Caching based on region. Anyone heard of that before? Caching client. So you can cache in the client as well. I would say that depends on the use case. I mean, everything depends on the use case, but more often than not, I would say, like, if I'm in an interview and someone's like, oh, should I cache this on the client or something like that? I'd be like, Kind of goes without saying for certain obvious things. What I'm going to talk about is, let me give you an insight. So I don't know if anyone's old enough to remember pneumatic tubes, right? They put the message in the little tube thing and you throw it in the canister and it goes flying somewhere, right? The information being carried over a network is a physical thing like anything else, right? So the same way, if we were passing mail through a pneumatic tube, right, the further the distance between the sender and the receiver, the longer it's going to take for the mail to arrive. Again, sort of common sense, right? If I'm sending a letter to, the West Coast, or if I'm sending a letter to, Queens, which one's going to arrive faster, right? Especially if we're through pneumatic tube. Well, the electrons and photons that move over a cable, it's the same thing, right? If I send a message from New York to London, it's crossing over the Atlantic Ocean. Like that's far. So one of the things we can do is store the data closer to our clients, right? And so again, this is sort of similar to this idea of caching in the client, but not quite. Something called a content delivery network, right? Or a CDN. And it's networks of servers that are located in different regions around the world. And they essentially are caches for some of your content. So, and what you can do is send your user to hit the CDN first before hitting your servers, and they can get data potentially much faster, with much lower latency, I should say. Usually static content will be cached there. So what do I mean by static content? So media, images, video. Netflix makes heavy use of CDNs, right? There's no way they have a server sitting somewhere with all of the movies that you can possibly watch on Netflix, right? They've got copies upon copies upon copies of all the movies and shows that you watch, and they have them in different regions. So if you're in Europe, you're reading from a different CDN than you are if you're in the West Coast in the US. JavaScript tends to be cached a lot on CDNs. CSS, again, sort of open up a web page, all the things that you get in that initial burst just to build up the page. All of that is a really good candidate to be cached on the CDN. What is not great, right? Dynamic content. So what do I mean by dynamic content? If I go on to anything sort of personalized, right? Or if I'm going on Gmail, and this is gross oversimplification, but if I'm going on Gmail, right? The email that I have there, like say I have in a draft or something like that, I might not want to put that on a CDN just because, again, that's something that's going to change for me, and I can't be served to lots of different people, whereas like, again, whatever the new show is on Netflix, it's all basically the same for everyone. So that's perfect for CDN. Dynamic stuff, not so much, but if it doesn't change frequently, you can. And again, reduces latency. It also reduces the number of requests made to your servers, which is going to save you money. It costs you money to have a CDN, but often it'll pay for itself if you get a certain scale. Cool. Right. So the clients will make a request for some sort of static content. That'll hit the CDN first, again, sort of like another cache. And then if that content's not available, then it'll hit your servers. If it is, it'll just return directly from the CDN. And then any sort of dynamic content requests, again, like API calls, things like that, that's going to hit the load balancer. And then that'll just go through the normal flow. And again, maybe you've cached that data, so don't have to hit the database. But the idea is to sort of get the shortest distance between the client and the information that they need. Okay, anything more we can do? There's still a lot more, but I'm gonna, for the sake of brevity, identify performance bottlenecks and optimize the code. So that is such a great call out. a lot of the things that I'm talking about, I should put a giant, that statement is a qualifier for everything I've said so far. You shouldn't just go around slapping in caches and slapping in load balancers and slapping in CDNs just for the sake of doing so. You should do these things because they are because I'm reacting to essentially an issue, right? You don't want to prematurely optimize anything. You want to, sort of build something really small, test it out. Hey, I'm seeing that, the servers are starting to tip over, the app servers are starting to tip over because, the load is too much. Now let's scale those things up. So that's a phenomenal point. But for the sake of a system design interview, they're kind of just going to give away that, hey, we're going to be working on a scale that requires this stuff. And so, and we're going to get to that in a second, but basically there's a way to suss that out in the interview, and you can kind of assume they're going to want you to build something sort of kind of complicated like this. Well, my next question was, in what order should I apply these techniques? So I'm gonna get to that shortly. But I know I see we are okay on time, but I'm gonna move a little faster. So services, right? We can break up our application into smaller functions or domains called services and scale those independently as well. Here I'm going with this very generic sort of write service, read service. Let's say my application is much more read heavy than write heavy. So as you can imagine, with something like most social media like Twitter or Reddit or whatever, it's like 90% of their traffic is people just consuming. It's very few people posting and lots of people reading. And so if that's the case, maybe I can split up posting from consuming, or again, reading from writing into two different applications. And then depending on what it is that I want to do, right? If I'm trying to do I'm going to post a tweet, well, I can send that to a service that just handles posting of tweets. And then if I'm reading, I'm going to read just from a service that helps me read from the database. And so I have all those other similar things in place here, but now also my application is broken up into these smaller chunks. So this is, again, comes with cost, right? I can scale up different parts of my application independently. I recently spoke with someone who works at Netflix, and the team that they're on, they manage 15 services, just that team by themselves, and 150 other services consume their service. So when you're at like a Netflix scale or a Google scale, your application is broken up into lots of little different services that then all sort of talk to each other, and they're almost like mini little independent applications that can be deployed and scaled and work completely separately from other people. At Etsy, it wasn't like that. We had just one big monolithic application. So we didn't have this like write service, read service. It would just be copies of the entire app. But other companies, do they account for communication overhead? Yes. And again, this is one of those things where you should not do it unless you really have to. It's extremely powerful. And again, just the same way it helps with performance, it's also going to help with availability, right? If my write service crashes, my read service is still up, then people can still read tweets. They just can't create them for a little bit. And is that ideal? No, but it's better than everything being down. But communication overhead is very expensive in all of this and should only be done when you've hit a sufficiently large scale. Okay, so that was, I hate to I don't want to scare people, but I've just scratched the surface. This is just sort of, that was a list of things that I don't expect you to come away from this being like, I know load balancing now, I know services now. Those are essentially, take that as a list of things that you need to go and do some studying on, some reading on. Those are just the basic building blocks. It gets even more complicated. But as an entry-level person, no one's going to expect you to know all these things or have mastered all these things. But I do think having a vocabulary that will allow you to partake in some of these conversations and just, again, having this sort of template for here are the things that I need to go out and study and learn more on is going to help you. So don't feel bad if you don't know all this stuff. I've got 10 years experience and I'm only ever scratched the surface myself. So here I'm going to talk about a little bit more on, so now that you're in the interview, right? You know all the things that I've just told you. How do you apply this? How do you start the process of answering those questions? So again, a lot of times it's about the journey, not the destination, right? So sometimes if I tell you design YouTube, there might not be one right answer for how you design YouTube. Different people will design it differently, depends on the constraints. The interviewer also will sometimes play a little jazz and throw curveballs at you and just to kind of, so don't get too hung up on that. I think the main thing is your communication, particularly if you're demonstrating understanding of your decisions, right? So I don't remember where I'm going to get to that later. Well, I'll jump into that later. So here's a book someone told me about, System Design Interview. It's pretty good. It's on Amazon. It has a framework in it for how to go about answering these questions. And I've watched a number of YouTube videos of like folks giving example interviews, and they will generally follow maybe not this exact framework to the T, but something like it. So I think it's just a good starting place. And there isn't a perfect answer to any of these things. So this is the framework that the book offers. Essentially, there's 4 steps. And there's like sub-steps to each step. But first, it's going to be understand the problem and establish design scope. So what that means is ask a lot of questions and try to cut down on the stuff that you actually have to design. 2, sort of propose a high-level design and get buy-in. So the same way that, you know, if you were at work and someone wants you to build a particular thing, you want to find out information before it's too late, right? It's more expensive to make changes later on. So you want to start at a high level, get some buy-in, and then you move on to step 3, which is your design deep dive. That's where you really start to drill in on particular aspects of your design. And then 4 is the wrap up. It's just sort of making sure that you have covered all your bases, you checked all the boxes, and we're going to jump into each of these steps now. Someone asked any Udemy recommendations. I don't know if I've actually searched for system design in Udemy. There's a lot of really good free videos on YouTube. So I've only ever really looked at YouTube videos. So step 1, right? Understand the problem, establish design. So there's this notion of functional versus non-functional requirements, right? So what do we mean by functional requirements? Fancy way of just saying what the system should do. Right? So here's where we want to narrow down what the system does as much as possible. Right? So if someone comes to me and says, design Twitter, you know, how many different parts of Twitter are there? You know, if you really think about it, you have your timeline, you have followers, you have DMs, you have search, you have media, authentication, like, and I could keep going, right? So does the person want me to design all of these things? That's a lot. You know, maybe they only want me to design just, you know, being able to tweet and being able to search. Maybe they don't want me to do DMs. Maybe they want media, maybe they don't. Authentication, is that something that we really need to talk about here, or is that not what you're super interested in? So again, make sure you talk to your interviewer and say, what is it exactly that you want me to do? And don't do extra work because it's just going to waste time. And then you want to explicitly list the use cases that you want to cover, right? So logged in users, right, would be treated different from logged out users, right? Because a logged in user can post a tweet, can send a message, but a logged out user can't post, they can't send, maybe they can just read. So these are all things that you want to get explicit instructions on in the beginning. And then you want to define the non-functional requirements, right? Which is a fancy way of saying how the system should work, as opposed to what it should do. These are just some of the categories, let's say, of things we might ask about. Performance, reliability, scalability, availability, security, like. It's hard to say what are the specific ones you should ask on every interview. It kind of changes a bit, but here's just sort of a safe bet for some of the things that you might want to ask. And so make this a little bit more concrete, right? So a functional requirement could be something like users can post tweets, right? Whereas a non-functional requirement might be, we want a latency below 200 milliseconds, right? So functional is what they can do, and non-functional is how. Consistency, eventual consistency. That's a whole topic. I would highly recommend folks read up on that. So in a distributed system, and what I mean by distributed system, right, is just any system in which the processing occurs on more than one computer, right? So if I open up my phone and I add two numbers together in the calculator app on my phone, I wouldn't call that distributed, right? But if I were to use a web server to do that calculation for some reason, I send a GET request to some service and I say, add these two numbers up, and then it does the computation, it sends it back to me. Well, now the processing of that is distributed, right? It's happening on more than one system. Anytime you have a distributed system, which is what we've been talking about this whole time, right? Having lots of different servers, having app servers, having databases, you can only guarantee two of the following. So you have consistency, availability, and partition tolerance. Consistency means when I do a read, I get the same data for all the users, meaning, not that if I say distributed, not correct, distributed does not necessarily mean parallelized, right? You can do distributed processing serially. They tend to go together, but it's not necessarily the case. If you have 10, laundry machine, washing machines, right? You have 10 bags of laundry, like that's good, but some tasks can't be parallelized. Trying to think of an example. Yeah. There's if I'm baking a cake, right? I can't do step 8 before I've done step 2. Like there's just no way to parallelize. So, so in the distributed system, you can only following, right? So reads return the exact same for all users, consistency. That doesn't mean that if I read, my name, that you're also going to get my name. What that means is, if I ask for a particular piece of data, that data is the same for any one user. So if I want to know what the latest stock price is for, Apple stock, if every user who makes a request to the system gets that same number, that means we're consistent, right? But if we have a system where we have a lot of distributed database replicas and they're not all in sync with each other, and then maybe I get a slightly stale read, but you get an up-to-date read, well, that's inconsistent. Availability, right? Every request receives a response. So, we want to make sure that we are allowing for time check 30 minutes. Thank you. We want to make sure that we're allowing for, we're going to always respond to a request with something, even if it's not necessarily the most up-to-date data, but we're going to respond with something. We don't want to block anything. And then partition tolerance, right? If I have 2 nodes and one of them goes down, or one node can't communicate with another node, I still want to be able to respond in some fashion. I'm kind of trying to oversimplify this a little bit, but I hope everyone's with me on this. So why can you only choose 2 out of 3? So for distributed systems, partition tolerance is considered a necessity, right? If a partial outage occurs during a read or a write, your system must continue to operate. Sort of considered like not really a choice here. So that leaves us basically with only being able to choose either availability and partition tolerance, or consistency and partition tolerance. So which one do you choose, right? Why is there friction between these? Well, let's say an outage occurs and a write comes in. Now I can't sync that write to my entire system because one of the nodes is down. So what do? Right? Do I just cancel that operation? Say, I can't write it to everywhere, so I'm not going to write it anywhere. Well, that's going to decrease my availability, right? My availability is that I'm always going to respond to a request and handle it and do something. What about if I do write? And I say, you know what, eventually I'm going to update that node that's down, but I'm going to write to everywhere else that I can. Well, then if someone reads, right, there's this chance that they're going to get that stale piece of data. And so I have to pick one or the other. I can't really get both. This is kind of a tough one to explain as quickly as I am, but I hope it makes some sense. And again, this is a super important idea. I highly recommend folks read up more on this. So during interviews, you're going to want to be explicit about the choice that you're making, right? Again, you don't have a choice really with partition tolerance. So your choice is really between consistency or availability. And you're going to want to choose consistency over availability when data integrity is high, right? So financial transactions. I would not want my bank to show me two different values for what my balance is. I want that to be consistent. I would be okay with my bank telling me, you know what, we can't process your request right now. Sorry, rather than partially writing that information. Whereas something maybe a little less essential, right? Like, two users seeing a different number of likes on a tweet, that's probably okay to me. Eventually we can work that out and it's not that big of a deal. So in those situations, I'm going to want to choose availability, right? When I just want to make sure I'm always responding, even if I can tolerate some inconsistency, then I'm going to choose availability. If I can't tolerate any inconsistency, then I have to choose consistency over availability. Essentially, I'm going to have to block certain reads and writes from occurring. Cool. So finishing off step one, or almost finishing off step one. This is probably my least favorite part of this framework. I've always found this to be not the most useful thing because the scale that they're asking about, I don't know that these numbers really, for me, inform all that much. I'm just going to throw on all the bells and whistles they ask me. But maybe somebody who knows better than I would disagree. But they'll want you to do what we call back of the envelope estimations. They can help you get a feel for which designs will actually meet your requirements. So like load, storage, resources, network bandwidth, and I'll make this a little bit more concrete. So let's do back of the envelope estimations for Twitter. All right, so here's assumptions. I'm going to line up what are all the different assumptions that I can make about Twitter for the sake of this interview, right? These numbers don't have to be perfectly accurate. So either myself or the interviewer could say, you know what, we're going to use 300 million monthly active users, right? Maybe I Google it and I see, okay, that's how many users Twitter has, or maybe the interviewer will just offer that information to me. And some percentage of those users use Twitter daily, right? Not 100% of them, so half. Users post 2 tweets per day on average. Again, I have no idea if that's accurate. It's for my back of the envelope estimation. So 2 is a nice number. 10% of tweets contain media, right? So that's something that we might want to account for. And we have to store data for 5 years. So these are my base premises that I have to work on. So now let's actually start to do these estimations. Right? How many queries per second, or is this system going to have to handle? How many requests per second? So we take our daily active users, right? 300 million, cut that in half, right? Because only 50% of users post daily. So that means about 150 million users interacting, on a given day. So we take that 150 million users posting 2 tweets a day, right? But we're going to spread that across the 24-hour period and divide that out into the number of seconds. And so we'll get about 3,500 requests per second. And then peak, right, would be if every single user could possibly sign on at that particular moment. So we have to times it by 2, right? Because 300 million is our ceilings. Now we have 7,000 queries per second. And let's talk about media storage, right? So the average tweet size, a tweet ID is going to be 64 bytes. Again, these are just, you do enough of these and they kind of, you'll come up with good estimates and guesses for what these things should be. It used to be 140 characters, right, in the tweet, and 1 byte per character, 140 bytes. And then let's say media, again, let's say the average tweet that has a photo or something has a 1 megabyte, picture associated with it. So how much media storage do we need? Well, we have 150 million posting 2 tweets a day. 10% of that have media, right? And then we have to times that by the average media size, and we get 30 terabytes a day. So over the course of 5 years, that'll be around 55 petabytes. So what does this all tell me? This all tells me that there's no one system that's going to handle 7,000 queries per second. There's no one physical server that's going to do that. I'm going to have to scale this thing pretty wide. And then as far as media storage, again, database is going to have to be pretty substantial. Again, I'm not just going to be able to install MySQL in this one particular instance and I'm done. So step 2, we're going to propose a high-level design and get some buy-in. So you're going to sketch a diagram of your system's core functionalities. And here you want to kind of start a little smaller. You don't necessarily want to throw everything in just yet. But it's generally pretty safe to talk about having different services, having the load balancer, and having caching. Those are pretty like standard. CDNs is more of like a specific thing that you might need depending on your circumstances. If they talk about being geographically distributed and stuff like that. But you want to refer back to all those requirements that you gathered as a sort of checklist, right? And so if I go back to my functional requirements, right? Users can post tweets, users can delete tweets. I want to go through that checklist, but do it on my sketch and just make sure that I'm accounting for all of those things. Like, okay, what's the flow? A client sends a request to send a tweet to the load balancer, and then the load balancer hits the write service, and then the write service is going to write that to the cache and to the database, and then another user comes and reads that tweet, so then it's going to send a request to the load balancer, so on and so forth. You want to define the API, right? So what are the endpoints you'll have to create? So we talked about that weather API. So now we're designing the API for Twitter. So I'm going to say, you want to get a tweet, you want to read a particular tweet, you're going to have to send a GET request to /tweet. The parameter you're going to have to give me is the ID for that tweet. And then I'll respond back with the user who wrote it and the content of that tweet. You want to define your data model, right? So what are the tables that you will need to create in your database? What are the relationships between those tables? So again, here I just have a small slice. Here our tweets table. It's going to store, the tweet ID as an integer. That's going to be the primary key. I have my users table. User ID is going to be the primary key. And then in the tweets table, the user ID is a foreign key to users. In my likes table, the user ID is a foreign key to my users. And so just setting up these relationships, setting up what are the pieces of data that you want to track. And then again, it's sort of built into almost every one of these steps is this idea of get buy-in, right? I've given you the API, I've given you the sketch, I've given you my data model. Am I on the right track? Make space for them to interject. Always want to don't just go in there and just talk and talk and talk. It's not a lecture, it's a conversation. And you want to get buy-in and say, does this look good to you? Should I, is this the time to go all in on this? Awesome. So now we're finally at step 3. Right, we're going to want to do a deep dive on some part of the system. Sometimes the interviewer will tell you, like, you know what, I really want to talk about, database replication, or I really want to talk about, CDNs. We're going to have this media that people tweet, like if some influencer posts an image that everyone in Southeast Asia is going crazy over. Well, maybe we want to put that image on the CDN for Southeast Asia, right? So like these are things that we can kind of talk about here and get a little bit more into the weeds of our design. And again, database replication and sharding isn't just about robustness, it's also about speed. Technology choices, right? So what sort of database are we going with here? We're going to use a relational database, a NoSQL database. If we're using a message queue or event streaming, am I using Kafka? Am I using RabbitMQ? If this were a chat application, am I doing long polling? Am I using WebSockets? This isn't an exhaustive list by any means, but it's just sort of the point is that you should be aware of what your options are, and you should be able to discuss the trade-offs between them. And so if you're going to choose NoSQL over relational, why? Like, articulate exactly why you're making that decision. I can make a case for either one, and either one of those cases could be really compelling, but but if I can't say like, well, I'm choosing NoSQL over relational in this particular case because, and so just to give an example of that, choosing your database generally depends on what type of data you're going to be storing, right? So if you are storing very structured data, probably want a relational database. If it's very unstructured data, you want blob storage, semi-structured, NoSQL. What do I mean by structured, unstructured, semi-structured? Again, I don't want to go too deep into the weeds on any one thing. But let's say like structured data, right, would be very highly organized, very consistently formatted. Again, customer information, financial transactions. That's stuff that you're going to want to put in a relational database. Semi-structured data, so sometimes like your log files and things like that will be stored as JSON or XML or something like that. Has some internal structure, but maybe sometimes is more fields than not, or it can be a little bit variable. And then unstructured data, my image is clipped a little bit, but unstructured data is going to be anything that requires additional processing to extract meaning from. So images, video, that's not something that you're going to directly really deal with in a database. So you're going to use something like blob storage. 15 minutes. I think I'm almost done, actually. And then step 4 is the wrap up, right? So you're going to want to just kind of go over the design you just gave. You're going to want to discuss maybe possible improvements. A lot of times you're going to run out of time. You're like, oh, I didn't get a chance to talk about how I would have implemented search. I didn't get a chance to talk about, what I would have done, to speed up some particular scenario. Maybe start to go through and think about error cases, right? If a server fails, how are you handling that in your design? What metrics should you track? So again, this is starting to get a little bit more into like the sort of expectations of a senior engineer, right? Because when you've built systems and had to maintain them, keep an eye on them, you sort of build up this intuition of, okay, there's certain pieces of information I want to keep track of. HTTP response codes, right? Am I sending 200s all the time? What if I'm sending a lot of 500 error messages or 400 error messages? Like, I want to keep track of those things. How will you monitor the system? There's a bunch of different tools for that, like Grafana and Datadog and all these other tools that you can plug into your system in order to keep an eye on things. And then again, always make space for the interviewer to pick something to drill into. You don't want to just talk and talk and talk. It's a back and forth. They might have a particular thing that they really interested in, or they might have picked up on something that you maybe glossed over and they want to kind of drill into a little bit. And if you're going to take one thing away from all of this, the best tip I can give you you need to practice, right? You are not going to nail this. I don't care. This is how intelligent you are. I don't care how well read you are. This is not something, this isn't algorithms. This isn't something that you can just kind of think about and sort of know a priori, right? You need to practice giving answers to these interview questions. You need to practice different questions, design YouTube, design Twitter, design, URL shortener. There's a million different versions of these questions. You have a phenomenal resource of all of your classmates and all of the people around you. They're all, in a similar situation as you. They want help. You can help them. They can help you. Talk to people, practice. There's a website called Prant. It allows you to pair up with other engineers also looking for practice. You can do system design interview, and you can do algorithms and data structures interviews on there. Practice, 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 practice. And that's it. These slides can be found at that URL. I'll see if there's a way for me to also just send out this URL as like a link. But that's my talk. Happy to answer any questions or whatever you think is best.
Awesome. Thank you so much. Well, that went definitely into a more involved space than I as a student, but there was quite a bit of engagement, and I think there was a lot of information to be absorbed here. And as you said, this was literally just the tip, as it is a very layered, complex process. But we do have a few minutes, so if anyone would like to ask questions, I think Constantine put in some things, so maybe Carlos, go right ahead and share out for us, please, if you will.
Sure. So Constantine asked, can we come back to web server versus app server? What I saw as an explanation is that web server is very light, just accepting requests, passing over to load balancer, while app server is usually very powerful machine running the logic of the app. However, lots of times the architecture designers with this not follow. So you're on the right track there. The web server is this very thin layer that sits in front of your application. And its job is purely just it gets a request and it sends it off to your application somewhere. Those things tend to be housed together. I think that's why in my slides and a lot of slides you'll see they don't really distinguish between the two, because it's sort of just like a built-in assumption that the web server is sort of baked into your app. So maybe a good example. So Node.js, right? I don't know if anybody's experienced with JavaScript on the back end. Node.js is both a web server and an application server sort of together. You can write your application code and then launch Node directly, and it can actually handle incoming requests. But again, it's usually not the best idea to have those sort of sit together, because if one crashes, then they both crash. So what people will do, and this is where someone else talked about proxies and reverse proxies, what they'll do is they'll set up a reverse proxy, which is they'll set up an Nginx server, or again, a generic sort of web server that sits in front of their Node.js server. And then the requests come in, they hit Nginx, and then all Nginx is responsible for is taking those requests and sending them to Node. The reason people bother to do that, you can configure, Apache or Nginx to a really powerful degree, whereas with like Node, it's a very basic web server that you're not going to have as much control over, let's say. Trying not to get too far into the weeds on any one thing there, but I don't know if that answers your question, but it's your application code. Same PHP, I think, also could do something similar, right? I can launch a web server within PHP, or I can launch a web server within Go, but I'm probably not going to expose my raw application to the web. I'm going to put some sort of web service in front of it or web server in front of it as like a reverse proxy or something like that. Yeah, I'm happy to, if you want to email me or something like that, I can send some links out about like further reading on that.
Awesome, thank you. Also, Carlos, would you mind sharing the link either in the chat or if you want to send it to me directly? I will be sharing a closing email with all who've participated as well as all who've registered. Therefore, they can access it. Perfect, thank you. So for all of those who are here, if you'd like, the link is already placed within the chat, so you have access to it there. I'll also be sending a closing email, which will include today's session, the recording of it, as well as the link again, should you need it for future reference. And this is we have a few more minutes. So if there are any other questions that you would like to share out, definitely this is the time to do that. I think, Carlos, this was a great session, a beginning only for something that I would like for us to continue to develop further, and just to continue to provide to the students. And it seems as if we have quite a bit of interest. And so we'll definitely speak offline more about that. But for all of you who are attending today, definitely do be on the lookout for more opportunities where you can learn more about systems designs and um, other elements within the umbrella of the computer science realm. And then if there are anything that you're specifically interested in, we definitely try to meet students where they are in terms of level of interest. And so I would love to hear more about what it is that you'd like to have, an experienced professional speak on or more exposure to. Someone said machine learning system design workshop. So thank you for that, Constantine. I will definitely make note of that. And we will continue to see how much more we can provide for you. But Carlos, any closing thoughts?
No, thank you for everyone for attending and for your flexibility. Hopefully I was able to get through that as well as I could, given the circumstances, but yeah.
Thank you again. And Carlos, thank you again just for even initiating this. And I know you're not, doing the greatest with the COVID and all, still very present. So everyone still be very careful out there. But we will talk soon and I will follow up with a meeting as well as more upcoming sessions. So everyone, thank you and have a good one. Take care.
Thank you.